Hello, this is the Phase D Hydration Monitoring wristband, and this group is composed by Gabriela Lugo, Fabiola Pons, and Jose Martinez, also the Professor Alex Velez. Now I'm going to leave you with Fabiola that she's going to talk about the outline.
Hi. The outline for this presentation, which is the Phase D review. We first gonna start with the amendment made to the Capstone project for this specific phase, the system validation or objectives, the system level MOPs to verify or validate, then the validation and verification procedures, and then the system budget, and finally the project planning. Well, first we're gonna start with the amendments. We have the amendment number 1, which is this capstone was made by a simulation-based validation instead of a physical prototyping. The change made is that we are using basic simulations with synthetic data instead of building a physical prototype. The reasons for the specific change is because the project is remote and the team members do not have access to meet in person or to physical tools or materials. The second amendment is the simplified sensor data modeling, where we, instead of collecting real sweat data, we generate general sample data that simulates the hydration and dehydration conditions. The reason for this change is to allow us to test the alert logic and basic way without needing a real sensor. The third amendment is the general component compatibility check. When we review the component, the main component data sheet and the high level to ensure the voltage and communication type of match. This was because we can physically test the components together, but we can compare the data sheets to show that they can work together. The fourth amendment is the basic power estimation, when we did simple math using datasheet values to estimate the power consumption and battery life. And finally, the fifth amendment was the general benchmark comparison. When we look at similar hydration systems like the Gatorade GX patch and compare our expected performance in a basic way. This helps us understand our system concept is within a reasonable range of real product. Okay, the validation objective for this phase is to verify that the hydration monitoring wristband accurately detects the potassium ion levels in simulated sweat data, as we mentioned before, and triggers a hydration alert within 10 seconds when levels fall below the clinically defined threshold of 5 millimolars, thereby enabling timely user notifications and effective hydration management. Now Jose is going to discuss the MOPs for this specific phase.
As Fabiola said, now we have the system level MOPs to verify and validate our project. With the first MOP being the accuracy of the hydration status, the determination should be from greater than 90% from hydrated or dehydrated status. The latency for alert should be less than 2 seconds. The voltage and currents required comply with the recommended operating range, with the connection being fully validated via datasheet parameters. The output from the sensor is compatible with the microcontroller input method and with the data being successfully validated. The power consumption complies within the battery capacity, the project being or the device being at the 24-hour operation with one battery cycle. The comparison ranges from 5 to 10% from benchmark systems, as Fabiola said. The features, power efficiency, mobile sensing alerts, and etc. of other devices are fully functional and greater than 50% of our features with other established systems. The ease for users to calibrate the systems is less than 5 minutes, and the ability of a system to detect hydration under various temperatures and 0% data loss. These MOPs were also verified using multi-physics simulation. As Fabiola said, we can work the project together and physically. So we use a multi-physics simulation.
So this is the validation and verification procedure. First, we have the system simulations via modeling tools. We have the experimental objectives. So that means that we validate some mobs that we use for the system simulation. Those are the mobs that we use. And then we have the theoretical background. It means that simulations replicate sensors, input behaviors, and system response used in Python with NumPy and SciPy for signal processing and logic testing, simulated electrolytes values for hydration and dehydration, timing functions to assess response latency, and energy consumptions model using known datasheets value. Then we have the methods. We have the simulated sweat data generation, and then we also have the two conditions model that it will be the hydrated state and dehydrated state. And also we have the processing logic simulations, and in there we have the logic implement that it was a Python, and we copy that code and it's right over there. We have the power consumption estimation. Using datasheet value, we have the switch sensor draw, the Apollo 4, and the battery capacity. And the simulation estimated the device runtime and validated that systems operate less than 24 hours under normal conditions. And then we have the equipment and experimental setup. It was the software with Python, and then we have the synthetic database on sweat sensors range, the simulations of Apollo 4 microcontroller logic, and the visual timing tools for latency. Also, we have the estimated energy draw based on datasheets. The experimental procedures, we have 7 that they generate synthetic input data, simulate signal processing and decision-making logic, record decision output, measure time between threshold detections and alert trigger, and some estimated power uses over 24 hours with realistic duty highlight, and then simulate hydration signal behavior at various temperatures. And last one, we have introduce virtual noise or interruptions to test data continually. Then we have the data sheet. We see that the result, we pass all of them, and then we have the calculations. How do we calculate the accuracy, the latency, and the power and error rate? Now for the second one, we have the component datasheet analysis and compatibility tests. We see that we use 3 mobs that were mentioned by Jose, and then we have the method was the datasheets references, the sweet pot potassium, Apollo 4 Blue Plus microcontroller, and then the LiPo battery. We also have the electrical compatibility check, and with the sensor Apollo 4, and also with the battery. The communication interface, sensors output assumed to be a LAN, and then analog, and then Apollo 4 supports both analog inputs and 12C communications. The results were that all components operate safely within shared voltages range and communicated over compatibilities interfaces. The timing and the responsive simulation, we had the sensor response time was less than 10 seconds for change detection, and also for the Apollo 4. And the simulated delay from input detection to alert. Power budget validations, we made it for a sensor, Apollo 4, OLED screen, and the total system activate draw was approximately 70. The battery run time estimated within 150 capacity. Then we have the equal runtime. It was 8.82 hours. With duty cyclings and sleep modes, runtime can extend beyond 24 hours. And then the theoretical background, we have the compatibility is determined through analysis of operating voltage and current ranges from datasheets, the communication protocols, and then the battery life calculation based on duty cycle. We also have the equipment and experimental setup, the datasheet for the switch, the Apollo 4 and the battery. The manufacturer provides diagram and also the power budget spreadsheet. Then we have the experimental procedure, cross references operating voltage and current for each component, ensure communication method, calculate power draw of each subsystem, compare total current draw with battery rating, and validate load behavior using mock load. Then we have the data sheet. You can see also that those results pass, and we can see the calculations based on battery life and compatibility matrix. For the third one, we have the benchmarking against similar system. We have the mobs that we use, and we have the method. The method was benchmarks, sources reviewed, the Gatorade sweat patch, the EvoCore biosystems, the Green systems, and the academic studies. The simulated model comparison, we use accuracy, the response time, and the result. And the theoretical background, benchmarks are taken from known commercial systems like Gatorade and EvoCore, and then the equipment and experimental setup, research papers, product data sheets, and white papers, publicity, available videos and case studies, and then performance comparison matrix. The experimental procedure, we collect public benchmark for key metrics like accuracy, odors, latency, and battery life. We list and compare feature sets, simulates, calibrate a system and time process for users' readiness, and then we create comparisons table to illustrate percent deviation. We can see in here the data sheet that all of the results were passed for the goals, and then we calculations, we have the percent deviation and the feature match percent. And then there's the code that was needed from the program running simulating code. Now I'm gonna leave you with Jose, that he's gonna talk about the system budget.
Thank you, Gabriela. As Gabriela said, the system budget didn't change at all from our other phases of phase C. So pretty much we have the polycarbonate casing as estimated cost per unit being 120, estimated cost per 10,000 units being 12,000, the OLED screen 350 per unit, 35,000 per 10,000 units, the rubber button being 50 cents, estimated cost per 10,000 being 5,000, the silicone straps, the 250 and 25,000 per 10,000 units, the spring bars 25 cents each, 2,500 per 10,000 units, the LIBO battery $2, and being 20,000 per 10,000 units, the switch potassium ISE sensor $8, being 80,000, the Apollo 4 Blue Plus $3 and 30,000 for 10,000 units, the PCB custom design $5, 50,000 for 10,000 units, the charging port 50 cents, estimated cost per 10,000 being 5,000, the wiring and connectors and the adhesive fasteners 10 cents and 5 cents, the wiring connectors being 1,000 per unit per 10,000, and the adhesive fasteners 500 per 10,000 units, with the total material cost being 26 and 60 cents, and the estimated total cost for 10,000 units being 265,000.
Okay, finally, we have the project planning. In the top of the table, we have the phase D presentation task with the name of the member of the group that made each one of them. And we also have the different tasks for the following presentation, which is the phase F, and the phase F presentation date being May 16. We also have the approximate weeks where we are going to be working with the task. And finally, we have the written report, poster, and certification, which is the last assignment that is going to be at the end of the trimester. Well, this is the presentation. In this phase, we establish the verification and validation procedures that we can use to verify our Capstone project. And as we mentioned before, this project is made on an online course, so the members of the group can meet in person. Therefore, we needed to use simulation and other procedures to verify our project. Thank you.
Thank you.
Thank you.